Oh, you spoke last week? Oh, yeah. Go back and watch it.
You didn't miss much, I think.
Wow.
Nothing.
I can't know that until I watch it.
But if I tell you, you could trust me.
Wait, so
How was your trip, man?
that's good. Yeah, I made an 8 pies for a week. Then I spent a week recovering.
That's a good plan. And when are you leaving? So you're staying for one more week, and then
Yeah,
something?
next Friday more.
Okay. And then you plan to come back every now and then? So.
My plan is to get back as much as I can. You know, like maybe I'm ambitiously aiming for at least every month.
Okay, good.
That's nice. You sticking around for the holidays? Are you going back? Or?
Actually, stay here. Yeah, no particular plans. My brother is coming here from Italy. He's spending 1 week here with his girlfriend.
All right, should we get started?
Yep.
I think this is the last research seminar of the semester.
It's learning seminar.
Oh, I don't know. That's the last one of the two. Both, yeah. All right. Well, it's our pleasure to have Greg closing out the semester with part 2 around the Zilber pin conjecture for variations of structure.
Yeah, thanks for the introduction. So that's part 2 indeed. So were there any questions on part 1? Okay. Yes, there are some questions. So in part 1, I explained, maybe just like a super short recap. So I explained the link with the Zilber pin conjecture and the link with totally geodesic varieties in 2 settings. So in complex Boy quotients, where gamma is some lattice, arithmetic or not, and in the setting of MGN, or maybe, or in some sense, omega MG. So where, and I explain some of the link that these objects, these totally geodesic subvarieties here, or these kind of orbit closures here, and the totally geodesic subvarieties here are interesting from a dynamical point of view and things like that. And then some of the Zilber pin conjecture was connected to some finiteness results in this setting. So I hope there was enough motivation, and now I just want to turn to the general theory of the Zilber pin conjecture. So maybe I recall the Zilber pin conjecture for VHSs, and then state some results, and then eventually give a sketch of the proof of the geometric part of Zilber pin. So that in these settings, these totally geodesic subvarieties were positive dimensional. And from this algebra geometric, differential geometric, or dynamical viewpoint, the positive dimensional parts were the most interesting. So yeah, let me just recall. So the setting, we will always denote like SV, just right for simplicity, VHS. So what do we mean by this? So S, the smooth quasi-projective variety over C. So maybe think of it of its complex point even, and V is a polarizable at VHS and variation of Hodge structures. And if you're more inclined, you can assume also it's so that would be pure somehow. I mean, there are seen a lot of these things. Previous talks, but I mean, if you're more inclined, you can assume that it's admissible. Graded polarizable. Then variation of mixed Hodge structure. So this M is for the mixed part. And in fact, this more general setting is what's needed to take care of these objects here. Very well. And the goal was to study the so-called Hodge locus of SD. So yeah, let me start. Maybe I want to recall first of all the Zilber conjecture. And before doing so, let me just recall how we see the Hodge locus as the subvarieties of the Hodge locus as intersections. So how does this work? If everyone is already familiar, just let me know and skip a part. So from SV gives us two data. One is the so-called Hodge datum associated to SV, the Hodge datum. And the other one is the so-called monodromy datum. So what's the Hodge datum? It's just a pair GD, and if we need to be more precise, we will note it as GS, DS. But sometimes it really depends both on S and V. So maybe the better notation would be to keep V in the notation. Okay. So what's this? So G is the generic Mumford-Tate group associated to the variation of Hodge structure. So either it can be defined as with some Tannakian formalism, or it can be defined as some Mumford-Tate group appearing at a very general point. And V is an orbit under the group G, and it's the so-called Mumford-Tate domain. It's really like parameterizing all the possible symmetries allowed by G. So that's what Ben, I think, explained as well in the previous lectures. And the monodromy datum is something smaller contained in GD, so it's a smaller datum. It's denoted by HS and maybe D naught, which lives inside this one. And it's essentially the same thing, but HS is the monodromy, is the algebraic monodromy. Of SV, and DS is now an orbit. S naught is an orbit in D of the real points of HS. So in general, the general results. I think many of you have already seen these things, so I will not make this story too long. But the general result is that the monodromy is a normal subgroup of the derived subgroup of the Mumford-Tate group associated to SV. So this link, in some cases they agree, but of course, there's more information in this Mumford-Tate group. But nevertheless, when we will turn on to the monodromy part of the Hodge locus, so when we will look at the positive dimensional Hodge locus, we will work more naturally with monodromy data. That's like what makes the positive dimensional theory much easier.
So with algebraic monodromy, you mean that it's risky closed?
Yes. So algebraic monodromy means, so I see associated to the VHS, there's a local system, which is a representation of the fundamental group. So if you think that all these groups depend on a base point, on a very general point. So on the complex point of C, there's a base point, and this guy here, essentially they go in some sort of GLN C, so inside maybe GLB S, so that's a Hodge structure. And so there's a local system associated to B. And that I look at the image of this thing, I take the Zariski closure of this thing, maybe I see it as a rational algebraic group, and then I take the connected component of the identity of that. Up to passing to a covering, you can assume that this image is connected. So somehow the difference between the connected component or not won't play a huge role, but it's, yeah. it's kind of you algebraize this image by taking the Zariski closure and the component. Thanks. Yeah. If you have more questions, please let me know. So I think we've already seen the V corresponds to a period map from S to D mod gamma, where gamma will now be inside the integral points of G, and there will be a lattice. And given a subvariety, given an irreducible maybe to be more precise, I should identify this thing. So this object maybe lives in the definable category, but in general, this is not an algebraic variety. So given an irreducible subvariety Y in S, you obtain there is another VHS. Well, there's a VHS on Y, or maybe on its normalization. So we know it just denoted by Y, B restricted to Y. And associated to such object, we obtain the same thing, the Hodge datum and the monodromy datum associated with this thing. And at the end of the day, we obtain a diagram like this. So there's another period map associated with this thing, which will be Y, dy mod gamma Y. And this object maps naturally to D mod gamma, and S maps to Y maps to S, and this diagram commutes. And so here you have the period map associated to V, and here was the period map associated to V restricted to Y. So the commutativity, so that's some sort of functoriality of the construction of variation of Hodge structure from S to its subvarieties. And in general, we obtain that Y is contained inside psi minus 1 dy mod gamma Y. So, and these pre-images, they are algebraic subvarieties because this map is definable and holomorphic. So yeah, maybe I should give it a name. Say that's kind of in the holomorphic category here. We give a definition. Y is special if it's a component of this pre-image. So it is a component okay, and it's weakly special essentially the same definition, but if it's a component now with the monodromy datum. Okay, so I will give you some examples. Yeah, and yeah. So what's the first example? Let's take S equal to AG. Maybe I mean to make it a variety, maybe we add some level structure. So there is on AG there is a standard, let's say, VHS, making SV exactly a pair as we were describing before. So this VHS is just parameterizing the fiber. So the fiber at a point S. So a point S corresponds to an abelian variety AS. The fiber at S will be the H1 AS with coefficient in Z. So it's really like, in some sense, the variation of Hodge structure parameterizing the abelian varieties. So Y in S is special for SV if and only if is a sub-Shimura variety or a translate of a Shimura variety. So the idea is that to make the Manforty. So this definition is telling us that first of all, you have to make the Manforty group drop, and then you have to be the biggest subvariety with that drop of Manforty. And the sub-Shimura varieties are essentially given by sub-Shimura data, and these sub-Shimura data are parameterizing some sort of drop in the Manforty. And
It's obvious that Y is also contained in the symmetry of dy naught. Isn't it?
in the weakly special case, you mean?
In general, you mentioned
Yeah.
that, of course, Y is contained in the symmetry. But dy naught is a subsym of dy, so.
Yeah, but the difference in general is very small. I mean, they differ by a factor. There's no preimage essentially.
So Y is also contained in the.
Yeah, exactly. Yeah, sorry.
And so when you are special, the two are the same.
When you're special, you're also weakly special. That's right. Yeah.
Where do we see that weekly specials come in families?
Yeah, I will do.
Okay.
I will do it now. Yeah. Thanks. Yeah. I mean, let me go on with weakly special, and then you tell me the answers. Yness is weakly special. If and only if, well, there are various characterizations now. One characterization using the metric on AG, is saying that they are totally geodesics. Totally geodesic subvarieties. The other characterization is that they are maximal among even monodromy group. The third characterization is that they are bi-algebraic. And the fourth one is that they are of the form S1 cross a point, where you have S1 cross S2, two sub-Shimura varieties of S. This is a sub-Shimura variety. So I think this is what Jonathan was hinting to. So maybe even before we say that I should have remarked that every single point is weakly special. In that case, the monodromy datum associated with this is just the point itself. But now, and whereas like special points, I will give more example in a moment, and we will see what the special points are. But these objects here, I mean, when you look at the monodromy datum of a sub-Shimura variety, you could think of, I don't know, A1 cross a point inside A2. The monodromy datum, we see the point, the orbit will see the point, but the monodromy datum does not really depend on the point. But the Manforty datum will depend on the Manforty datum will depend on the Manforty group of P, in some sense. And the monodromy datum does not depend on the Manforty group of P. So here is where they come in family. It's exactly related to the fact that the Manforty group is the monodromy group is a derived subgroup of the Manforty group. But the Manforty sees this factor. And with this description, a weakly special, maybe one can remark that weakly special if it contains a same point. A same point would be the case where this is exactly a sub-Shimura variety itself.
When
So-
you say a point is weakly special, it's only in the case of Shimura varieties.
That's right, in this example, AG.
General.
Yeah, that's right. So in fact, maybe more general, I mean, that's, yeah, maybe, yeah, I mean, all this discussion is within this example. Yeah, maybe I should have remarked every point is weakly special. So maybe that's not so interesting. And then there are countably many Hodge subdata. And there are countably many families of monodromy subdata. Only because I'm thinking that D splits as D1 plus D2, and my monodromy subdata is D1 plus a point. And that's one family. So at each splitting gives me one family, but there are only countably many splittings. And yeah, we will give more examples. So in general, the Hodge locus of SV is just the union of the special subvarieties of S. And you can define the monodromy locus as the union of the weakly special subvarieties, but you see that this monodromy locus doesn't quite make sense because every point is weakly special, and if you do the union of all points, you lose. I mean, you just get S itself. So this motivates us to introduce the following definition: a subvariety, a subvariety irreducible Y in S is said to have a positive P dimension if psi of Y is not a point. Or if you want, I mean, this psi of Y still as a complex structure or even an algebraic structure thanks to the work of Ben and Jacob and Ivan Brumbard. So you can even speak of dimension of the image. But for this definition, you don't need to know much. And yeah, so the monodromy locus, you can introduce it as the union of special subvarieties of positive P dimension. And yeah, the other definition we want to make is to distinguish whether Y is typical or atypical. So when we were here, morally we were thinking that our special subvarieties Y were the intersections between S and dy mod gamma Y. So a special Y is typical if the codimension in S of Y is equal to and the codimension of dy on gamma Y in d mod gamma, and it's atypical if maybe I should have written side. If the codimension is strictly smaller than the object here on the right hand side. And with this, we can define the Hodge locus atypical as the union of special and atypical. And the Hodge locus typical as the union of special and typical. And yeah, and the Hodge locus is the union of the two. So it's time to state the Zilber conjecture. And at the same time, you can, if you have a monodromically special subvariety, you can define the notion of being monodromically typical or monodromically typical. And you have to pay attention about some subtlety in the difference between the two. Or maybe let's state the Zilber conjecture. So the Zilber conjecture has a rich history. So in the setting of Tori, you state it first by the special case appeared in the work of Bombieri, Masser, and Zanier. Then Zilber and Pink, with different motivations, consider the case of abelian like families of abelian varieties, Shimura varieties, and mixed Shimura varieties. It was motivated also by the work of André and Ort. And then in the VHS setting, there's maybe an old work of De Jong. Then Bruno Klingler was another one of the first ones that formalized a version of the Zilber conjecture, and then in its final form, it's studied in a paper of myself with Bruno Klingler and Emmanuel Ulmo. But if you want to know more about the history, please ask me. So the conjecture is the following. So there are only finitely many maximally typical sub-varieties for SP. So maybe two remarks, unless there are questions on the definitions and the statements. So two remarks, this maximality means maximal among atypical. So even though we were interested in the Hodge locus, when we turn to this conjecture, we kind of forget about this typical pattern. And the maximality is a notion only inside this object here. So maybe they're not maximal in the Hodge locus. And the finiteness is a set theoretic statement. So you can think of keeping these objects with more complicated, non-reduced structures, but when you do this finiteness, you're just interested in the set of complex points that you get from these atypical intersections. Okay, if there are no questions, I will give you a few examples that can be helpful to see the picture. But are there any questions? So let's go back in AG. Why is AG special? So maybe it's a question, is it typical or atypical? What is typical? Is always. So I will not do I think it's more useful if you think about it yourself and then you check that this condition is really satisfied. But I mean, the Hodge locus of a Shimura variety is only made by typical objects.
But you think about it in terms of the period map, not forgetting information, is it a good intuition or?
What do you mean? Not sure.
I call period mapping psi.
Yeah, but
Okay, so maybe.
Or is it
no, it's not about the injectivity. I mean, you can think in this game, you can think that psi is always injective. You just replace psi of S by its image, in some sense. And thanks to various results, you can assume that it's a nice behaved object.
So it's really the codimension.
Yeah, in some sense, a special subvariety. Yeah, this is really like this typical or atypical dichotomy. In some sense, here there's no intersection. So a special, yeah. So what? So okay. Let me do this writing. Special means a subshimura variety. So y is equal to y cap s cap ag inside ag. And this is a typical writing. In some sense, there's no intersection.
Okay.
So that's one example. So you take any SV, and you take P in SC, a CM point. So P is special. P is always special, unless the variation for structure was completely trivial, so completely isotrivial. So P is special, and P is typical if and only if S is a Shimura variety. Or maybe SP. So also, I mean, this is also another exercise that you should think about it. That is the same point kind of an intersection or not? It depends on the ambient D-mod gamma. Yeah. And if you take S equal to mg, and V the moduli space of curves, and V the VHS, the field map psi, the map from MG to EG, associating a curve with Jacobian. Then here there are both typical and atypical special sublattices. A typical example of a typical intersection is the set of Jacobians that split, that contain an elliptic curve, for example. That's a typical intersection. But to understand whether it's typical or atypical, you have to get familiar with this kind of dichotomy. So at first sight, it's not that trivial. More questions?
And what is an example in that case of atypical?
Yeah. If you use the previous point, you can get some examples, right?
Okay.
But so, I mean, if I wanted to cheat, this one gives an example. If you take P equal to Jacobian, x to the n plus y to the n, that's it. And but then this is not an example for every single genus G, so it's not so easy to construct the atypical intersection. But for example, if you had a Shimura curve inside MG, there would always be an atypical intersection, and you can construct more examples, but they require ad hoc construction. But like these are family of examples for many Gs. Just because it's a simple, it shouldn't be there. And another example, just to finish, is related to, you can do the same with the non-arithmetic locus. Of the moduli space of surfaces smooth of degree D greater than 4 in B3. So this is some sense if you are rather than a Shimura-oriented person, if you come more from like algebraic geometry and you consider these non-Lefschetz loci, you will see that they also exhibit both atypical and atypical behavior unless you're in degree 4. Okay. Are there more questions on this? So that's the first VHS example beyond Shimura varieties. And I will tell you more what happens in the going very slow. Now I will tell you about the difference of Shimura versus non-Shimura. So the main difference. But are there more questions?
Just when you say if and only, for instance, if I take the space of K3, you have atypical.
Yeah, no, in that case, it's again a K3 surface. It's again, sorry, a Shimura variety.
But really, it's open or.
Okay.
For Shimura variety, you mean open in the.
Yeah, you're right. I mean, in some sense, I'm not distinguishing the difference. I'm not distinguishing the difference between a Shimura variety and an open subset. So I could set up that from the beginning. I assume that the period map is proper. It's kind of a standard reduction, so I extend it a bit. But otherwise, it means that the period map is dominant onto a Shimura variety. You can also cheat if you want doing a Shimura variety cross P1. But what really matters is that you're right. So this would be more precisely dominant period map. Thanks. And I'm cheating in a lot of points, so you're welcome to spot. So indeed, to detect the difference between Shimura varieties and non-Shimura varieties, let me introduce the notion of level of a VHS. So the level is essentially the biggest integer such that if you iterate bracketing with g minus 1, 1, so g minus 1, 1, k times, you get 0. What I mean by this, so G is the Lie algebra of G, the non-48 group of SV. So it comes equipped with the Lie bracket, but it also comes equipped with the Hodge filtration, the adjoint Hodge filtration. Coming from a very general point, point X in S. So once you have a point you obtain on the Lie algebra of G, you obtain a Hodge decomposition, but since it's the adjoint, it will be of the form, so it will be, maybe this was over Q, so GC will be of the form G minus N plus G minus 1, 1 plus 0. And as a level, you would like to take this integer n, but it's almost the same. But in some sense, you can be cheating when you do this. And so essentially, you look at the smallest sub algebra that you obtain generating by g minus 1, 1. And g minus 1, 1, in virtue of Griffith's transversality, plays a special role in the theory. Now, the images of period maps coming from S, they will land inside g minus 1, 1. So, yeah. And not here, so Shimura varieties means almost level 1. And this case here, if d is bigger than 4, then V has level 2. And yeah, you should think if you had an HN there, this should have level n, unless some of the odd numbers are 0 or very small. And the theorem.
So here the level is the smallest image of the period map is inside the period domain.
That's right, because you have more. Because when you take, so when you have S psi in the mod gamma, you take your point X here and you deep psi at X, the tangent space of S will lie inside G minus 1, 1. And somehow, so you know this, so the longer your tail is, the smaller you are. Exactly. But that's exactly also the intuition behind the following theorem. With Emory-Ullmann-Bruno-Klingler, that if the level is bigger than 3, then the Hodge locus typical is empty. So there are no typical intersections. Exactly because the idea, as Anna was saying, is that you are very small inside the period domain. So the smaller you are, the bigger, the easier it is the harder it is to have typical intersections. But there's an argument behind it, and maybe I was planning to say it, but maybe I will skip it. So in level bigger than 3, so Zilber pink here predicts the qualitative behavior on the pole of Hodge locus. So you can skip this atypical or typical dichotomy if you had if you were looking at varieties of dimension n and bigger or equal than 3, and you're looking at an H3 or something like that, the Hodge locus will be only made of atypical objects. Okay, so maybe section 2. What can we say? On HL, atypical in general. But one famous, so I was saying, I was hinting to before that I want to talk about this positive dimensional part, and I want to explain you the link with some beautiful results coming from functional transcendence due to Ben and Jacob and other people. But before I do so, inside this notion, inside this game, there's also the arithmetic part of the conjecture, and these cases are mostly known in the setting of Shimura varieties, and maybe the most famous example is the Andre-Orth conjecture in the final form, proven by Jonathan, Jacob, and Anna, and which was the special case of somehow the distribution of CM points. Very well. So what's the statement? So I will talk about the geometric, the so-called geometric part. And maybe, so this is about HL80, but now pause.
Can I just ask,
Yes. Yeah.
would now be the time to ask about level 2? In level 1, everything is typical. In level 3, everything's atypical.
No, in level 1, you have both typical and atypical. Like for the example of AMG, you have both examples of typical and atypical. So like a CM point will be atypical, but the intersection, the set X in MG, such that the Jacobian of X contains an elliptic curve. This one is typical. But you're right that in level bigger than 3, everything is atypical. So it's a good question. So what happens in level 2? Again, in level 2, even in this noted-lattice locus, you will have both phenomena appearing. So you will have both typical and atypical intersections. But in some sense, the typical intersection should be slightly less typical compared to the level 1 case. Yeah. So, but I mean, I don't know a good way to formalize it. Apart from using that, you have this condition.
Sorry, so what is the relationship between being Shimura and being level 1?
It's the same thing.
But I thought you said that every spectral subvariety is typical in a Shimura variety.
Yeah, that's right. But that's right. But there's a difference between doing this game. There's a difference between doing this game on S. So the Hodge locus of S, the Hodge locus of a Shimura variety. Yeah, you're right. Maybe there was confusing notation, is equal to the Hodge locus typical. But if you have a subvariety V inside a Shimura variety, then the Hodge locus of V is typical and atypical. And this one is not necessarily empty. It could be empty sometimes, but it's not always empty. So in some sense, yeah, that's maybe an important point. In level 1, you have the case where you can do the Hodge locus of the full period domain. In level 2, you don't have that, and you are always in some sort of mixed case where you do consider intersections. But so the example to keep in mind is that one thing is to do the Hodge locus of AG. In some sense, it's easy. The other thing is to do the Hodge locus of MG, where you intersect subvarieties with MG. And even though the associated VHS is of level 1, you are not in the case where the period map is dominant. So there's an extra layer. So there are two layers. Like first of all, your Shimura variety is your period domain is a Shimura variety, and the second condition is that your period map is dominant. For example, Andre-Orth says that if you have a dense set of CM points, your subvariety is, well, the VHS is of Shimura type, and the period map is dominant. So there are, like, in the general setting, there are two steps. First, you figure out what's the period domain, and then you figure out whether you dominate it. So, yeah, sorry if it was misleading before. That's a good point. Thanks a lot. Is it clear?
thank you.
Thanks. Very well.
Can I also ask?
Yeah, please.
So like the naive notion of level is like half the whatever amplitude of the Hodge filtration or whatever on the Lie algebra.
Yeah.
So how, I mean, that's bigger than this, but how far off are they? Like, in general?
You mean if I don't take the adjoint? Roughly.
No, take the adjoint, but just.
Okay. Even though
this could operator be smaller.
Yeah. So let's see that the most embarrassing case. Let's see, you look at the period domain parameterizing Hodge structures of with Hodge diamond 10, 0, 0, 0, 10. I think in this setting your notion will have level 1, right? But then you're right. But then there are no non-trivial. I mean, so in this setting you will have level 1, but this guy here will be 0, and then I will be forced to. I want to consider this example of level 0 in some sense because I don't have maps inside this period domain. And then once you have these bad boys, you can always give me any Hodge datum, add one of those, and make my level theory mismatch. And so I want to make this kind of more normalized thing that really puts the emphasis on G-1,1 because it's gonna be better in some sense in this theory.
What if like none of them are 0? Can it still be like very much smaller?
Well, I could add this one to something else, right?
Well, I mean, you're taking a very. Oh, I don't know. Anyway, yeah.
Well, but even if I take a very general point, okay. Unless the notion is almost the same. Yeah, you're right. Unless some kind of clearly wrong examples, everywhere else the two notions would agree. Yeah, you're right. Whenever you have enough monodromy, this example will actually recover the notion that you propose up to dead factors. So if your group was simple, you're good to go. Maybe absolutely simple. Yeah, that's right. Yeah, good example. Yeah, good point. Yeah. So in practice, what Ben was saying is that in practice you don't have to do. Usually you don't have to do this bracket computation. It will be kind of evident what you get. Very well. Let me give you the theorem. So maybe let me first give you a special case, and then I will explain the proof. So if the adjoint part of G is simple, then the Hodge locus atypical is not Zariski dense in S. Yeah. So you need this simplicity exactly to take care of this family of examples. So in general, let me give you more like kind of a loose statement. There are only finitely many families of atypical of maximal atypical positive dimensional subarrays. And you do need some family version because otherwise, like if you were state Zilber pink just with the positive dimensional condition, it will look like it. You can prove the full Zilber pink by proving a geometric statement just by adding a silent factor on the game, and then you would alter the dimension without actually doing anything. So you need this kind of you do need the possibility of fibering over something. And so these statements also have a long history, maybe. Well, in some sense, the first example appears in a paper of Jonathan on Y1 to the N. There's a paper of Emmanuel Ulmo in special case, a paper of Do, Ren, other papers, then another approach proposed by Do and Bignamini. And then there's the approach in the setting of VHS is given by myself with Bruno Klinger and Emmanuel Ulmo. And the most general one for mixed VHSs. So there were some cases done by Xiang Gao, and then the last one done by myself with David Urbanik. Let me just Ideally, I want to explain you the proof and the link with functional transcendence, all these in 10 minutes. Any questions? So maybe let's start with the section called functional transcendence. That also goes by the name of Affine theorems. Maybe just AS. So let me give you, maybe it didn't insist enough that when you have an Hodge link in D, so D mod gamma is a definable object or like it has many properties. D is kind of a semi-algebraic object, it's not the form GR plus model compact subgroup, but it sits inside the check, an algebraic value, a complex algebraic value that you obtain by kind of forgetting the positivity condition of the polarization. So, for example, the Ziegler space is just so let me give you the theorem done by Baker and Zimmerman. And it's the following. So you take, let's say V, a subvariety of S plus D check. You could think for most of the application, you can think that V is actually a product of the two subvarieties. And it's an algebraic subvariety. You take U, an analytic component of V cross now the graph of some of the period maps. So it's like the graph of S and D over D mod gamma. So this is kind of the pullback of the diagram. This piece here. So yeah, you're kind of intersecting with the points that gets mapped to the mod gamma to the same object. So you take an analytic component of this one, such that if the codimension of U in this product is strictly smaller than the codimension of the objects you use to intersect, so the codimension of V in S check plus the codimension of S cross. Then the projection of U to the base S is contained in a strict weakly special subvariety. So in particular, it's not Zariski dense, but also you get kind of a description of what you got. So you're inside the Hodge locus of S V. And strict just means that, I mean, maybe with the definitions I gave before, maybe S is always special or weakly special, and so you throw away this S from the game. And there's also a more general version. Which works in P over S, the period torsion. And this dimension here is kind of replaced by the dimension of G itself, rather than some quotient of DMG. And this object here is replaced by an opportune leaf of this foliation, of the foliation induced by the Gaussian connection. Okay. Any questions, remarks? Let me give you the rough idea in 5 minutes of the theorem. There, hiding values. Probabilities. So rough idea. Of symmetries helping. So the first step is notice that in P check for P, there are only finitely many families of weakly special subvarieties. Or of weakly special Hodge data. So, like, if you take y1 plus y1, you have to parameterize in a family all the Hecke correspondences yn, and clearly the degree goes to infinity, and there's no way to parameterize them in an algebraic way. But if you were to parameterize these Hecke correspondence yn inside the universal covering, so inside H cross H or P1 cross P1, in fact, you can parameterize all of them inside an algebraic family. So by working the universal covering, you pass from discountably many to finitely many families. And so, in fact, so there's a family, let's give it a name, F from Y to Z. So all fibers here appear to be weakly special subvarieties. And every weakly special in S appears as, let's say, pi of f minus 1 of z plus L. So let's say I do it in P. So I take the preimage of the subvarieties, I intersect with the opportune leaf of this foliation, that's roughly accounting for this thing, and then I project them back. So I have a recipe to construct all those locus starting from all the locus I have to consider starting from one fixed family. And this finiteness, yeah, well, you have to prove it. So it comes from the fact that after conjugation, there are not so many groups, subgroups, up to real conjugation. Okay. For each integer e n, you can define a locus sigma f e. So is an integer, f is the previous family, just the set of points x and y inside P cross C, such that the local dimension at x of the leaf at x intersected with the y is bigger or equal than e. So you consider this loci because then this is just kind of some sort of complicated parameterization in D of all Hodge loci. And now we want to stratify them by looking at the dimensions in order to single out the atypical Hodge locus eventually. And the point is that this object here is a constructible set. In the sense of algebraic geometry. A subset of the gamma. Third step of the strategy that we need to show that in the atypical range, so in the atypical range means that when you pick E in such a way that this intersection here is atypical, in the atypical range, we want to show that the projection to S of sigma Fe is not a risky answer. And in the atypical range, we can apply at channel. So at each fiber by fiber in this atypical locus, so whenever we have a point here, we can apply a channel and see that the projection lies in a strict weakly special subvariety. And we know that there are, as we were saying before, there are not too many options for the weakly special subvarieties. There are only countably many such. And we apply a channel to see the use that it lies in countable union of subvarieties. And the first step to conclude is that if you have a constructible set, the final step is that a constructible plus countable is finite. So this argument together, it tells us that the projection, once you're in the typical range and you start the game in the opportune way, I mean, in this step, I'm oversimplifying massively the picture, but okay, give you an idea, it's telling you that you will only have countably many. It lies in a union of countable subvarieties, and when you have a constructible set that sits in a countable union of subvarieties, in fact, it has to be equal to a finite union, and that finite union is not Zariski dense. Finite, so not Zariski dense. Yes, as we wish. And let me just add one sentence that there are also ways to do this argument rather than in P directly in D check, and rather than using constructibility, using ominimality. And eventually it's there's always like a step where there's an over-parameterization of the Hodge locus. This over-parameterization tends to be definable, and then a channel makes this definable set to lie into a countable union. And it can be can be confusing at the beginning because you start handling handling a countable set in some sense. You lose countability, but you make it definable, and then you recover countability through a channel. But a priori it was just countable, but not definable, nor sitting in any constructible set. So the idea to keep in mind is that countable, but complicated. We describe them either in a constructible way or in a definable way. We use the atypicality to make it again countable, this over-parameterization, and then either algebraic geometry or the very axiom of minimality gives us a finite result. And this finite result means that's not Zariski dense. That's roughly the idea. And I will stop here.
Questions?
There's some version of Zilber pink conjecture where the number of maximal atypical components is bounded by some data, or
yeah, in some sense you could make this proof uniform if you want. So you could fix some say you were inside a Shimura variety and you were fixing the degree of your subvariety and the dimension of your subvariety, then you could say that the number of maximal atypical components depends only on the degree of the dimension. So there are results like that. And if you want to know more, in general, maybe there are abstract results saying that these proofs can be made effective in some sense, but there's no clear-cut answer. So there's no it would be difficult. But in some sense, in AG, if you have AG and you have a bunch of same points, you can always construct a subvariety passing to those same points. That's by knowing that I have 1,000 same points, maybe it's clear that you need to make the degree grow, but it's not so clear how to give a very satisfactory and useful answer to that question. But if you're happy with steps in that direction, there's something, but there's nothing close to it.
In the geometric part that you considered, with Chris, though, we do give a bounded just polynomial in a degree, right?
Yeah, that's right. Yeah.
You can, yeah, it should grow with a degree, but it grows polynomially, which is what you expect. You can do better than that.
No, I
That's a good
agree.
example.
No, yeah, absolutely. I agree. Yeah, I agree with that. But in some, yeah, but in some sense, like if you take this example of MG and you expect no subshimura varieties at all, so there are examples of things you can say there are not too many exactly, but I mean you will not have an answer like if you expect there are none, you won't have an answer that tells you like no, there are no subshimura varieties, right?
Sure.
Yeah, but
By the
yeah.
way, in this mixed case that you said your newest result with urbanic, do you also have? I mean, what is there some problem to carrying out this like effective bound with polynomial in a degree, or I mean, I don't think you stated it, but I didn't know if there was any issue or you just didn't think about it.
No, I think it can be handled in a similar way. But the abelian case it becomes, I mean, the way these finitely many families are constructed is like, I mean, normally maybe you would think that there are only finitely many groups up to conjugation, and that result is not true anymore. It's like I mean, you can have a lot of the group might look like GA to some power, and then you have a lot of subgroups. The picture is slightly different, but many of the techniques apply in that setting. But that's a little bit of an oversimplification. I mean, this type is much harder. Because its construction it's not so honest.
Actually, I also have a mixed question. Is there in the mixed setting, is there some version of this like automatic atypicality thing?
Yeah, that's a good question. Yeah, I thought about it. Yeah, I mean, this. Yeah, I don't have an answer. I would guess so. This thing comes from the fact that if you have a subly algebra H and G, and H minus I is equal to G minus I, or I equal to 2, 3, and I mean they are non-zero for I equal to 2, 3, and so on, then in fact H is equal to G. And it's just a pure Lie theoretic result. So now you can wonder if you had another weight filtration and you had more, like maybe the weight was much longer, it would imply a similar philosophy. So it's maybe it's like, even if you had the pure part is level 1 or 2 and the mixed part is like very complicated, maybe you can run a similar game on each pure part of like really see how deep the weight filtration is. And yeah, I think that would be an interesting problem. But as far as I know, it's not known in the literature. Yeah, but I would guess that there is a state.
Other questions? All right, let's then bring again.